The night feels a little wider when we think about the worlds that circle our sun, far beyond the ones we learned about in school. Out past the familiar glow of our own sky, there are four immense neighbors, built not from rock and soil, but from cloud, storm, and deep hidden layers of gas. Jupiter with its ancient whirl of storms, Saturn with its fragile rings, Uranus turning on its side, and Neptune keeping quiet watch at the edge of sunlight's reach. Tonight, we'll wander out to them together, slowly, like following lanterns down a dark hallway. We'll trace how they formed, what swirls beneath their clouds, and why these distant giants quietly shaped the story of our solar system more than we were ever told. If this gentle drifting through the outer worlds brings you a bit of calm or wonder, a soft like and a quiet subscribe, help others find their way here too, only if it feels right. When people talk about Saturn, they often start with the rings. But if you listen to the quiet conversations between astronomers, there's another name that comes up just as softly, just as often: Cassini-Huygens. It's hard to put into simple words how fortunate we were that this mission actually happened, and that it worked for as long and as beautifully as it did. 4 robotic visitors have made their way to Saturn, but this long-lived, patient traveler changed what we know in a way the others simply couldn't. Its observations became the foundation for thousands of scientific papers, more than 4,000 careful attempts to turn faint signals and silent images into understanding. Along the way, it discovered new moons, half a dozen small worlds that no one even knew were there, and helped us see old moons with new eyes, their surfaces and insides suddenly less mysterious. Cassini wasn't just a quick flyby, taking a handful of snapshots before rushing on. It lived with Saturn. The spacecraft spent about 20 years in service, tracing a path of roughly 7 billion kilometers through the dark, and 13 of those years were spent looping, again and again, around the ringed planet itself. Orbit after orbit, it listened to the pull of Saturn's gravity, traced the shape of its magnetic field, skimmed past the rings to weigh them, and felt out the planet's internal structure by watching the tiny ways its path was tugged and nudged. It stayed long enough to see seasons change, storms grow and fade, and moons wander through their orbits like slow, patient actors on a dim stage. Right up until its final hour, Cassini kept working. Even as it tilted its orbit to dive between the planet and the inner edge of the rings, even as the atmosphere thickened around it, the spacecraft continued to send back measurements and images. In its last moments, as it sliced into Saturn's upper clouds into that deep, mustard haze that hides the world beneath it, transmitted everything it could until the heat and pressure broke it into countless fragments. Its body was destroyed, but the data it recorded remains, stored in servers and notebooks and minds, still being unpacked and puzzled over. Those bits and numbers are quiet, but they hold weather, chemistry, gravity, and time. And then there are the pictures. Cassini gave us some of the most peaceful, awe-soaked views of Saturn and the wider solar system that humans have ever seen. Rings turned into thin threads of silver, moons casting tiny shadows, the planet itself lit from the side, looking less like a ball of gas and more like a lantern held in a gloved hand. Through its cameras, Saturn stopped being just a diagram from a textbook and became a place distant, stormy, but somehow gentle to look at, like a candle seen through frosted glass. For a mission like that to exist at all, something had to start the story. The first robotic visitor to Saturn wasn't Cassini, but Pioneer 11, which swept past the planet in 1979. That small probe didn't stay long, but it did something quietly important. It confirmed that Titan, Saturn's largest moon, really had an atmosphere. Not just a wisp of gas, but a true, thick blanket of air wrapped around it. That single discovery lit up imaginations. A moon with an atmosphere could have weather. It could have clouds, lakes, maybe even a complicated chemistry that hints at the building blocks of life. Scientists knew they had to go back, and that next time, they wanted more than just a passing glimpse. They wanted to send something that could actually land there. By the time Titan's atmosphere was confirmed, 2 other spacecraft, Voyager 1 and Voyager 2, were already built and on their way, locked into their own grand tour of the outer planets. They couldn't be refitted with a lander. The window had passed. So, in the quiet offices and meeting rooms where space missions begin, people started sketching a new idea, a large orbiter, to study Saturn and its system in detail, carrying a small companion that could detach and descend through Titan's clouds. That partnership became Cassini-Huygens, named after 2 early astronomers who had studied Saturn through tiny telescopes centuries ago. It would be a collaboration across continents and decades, a mission designed not for a brief visit, but for a long companionship. Getting such a machine to Saturn was not a simple matter of pointing it and firing the engines. Saturn is far from the Sun, and the Sun's gravity is like a deep well in which the inner planets sit. Cassini had to climb out of that well. If it simply pushed straight from Earth to Saturn, it would need an enormous amount of fuel, far beyond what it could carry. So the mission planners used gravity itself as part of the engine. They sent Cassini on a path that curved around other planets, using their pull to steal a little speed each time, like a child using a swing to gain height by timing each push just right. After launching in October of 1997, the spacecraft did not head straight for the outer darkness. It first looped inward, toward the warmth. Cassini flew past Venus once, then again, letting the planet's gravity bend its path and add to its speed. Then it came homeward, back toward Earth, not to return, but to use our own planet as another stepping stone. Each flyby was a kind of cosmic handshake. The spacecraft fell toward a world, gathered momentum as it curved around, and then flung itself onward, a little faster, a little farther from the Sun's grip. This careful dance of slingshots depended on a rare kind of planetary alignment. The positions of Venus, Earth, Jupiter, and Saturn had to be just right so that one world could hand Cassini off to the next. That particular arrangement only happens roughly once every 6 centuries. If the mission had been delayed too long, the path would have closed, and the designers would have had to look for a different, less efficient route, or accept that such a journey might have to wait for another generation. Cassini slipped into that narrow window, catching the opportunity almost like catching a train that only comes around every few lifetimes. The Earth flyby, the second time our world and Cassini crossed paths, was especially close. At its nearest, the spacecraft skimmed about 1,100 kilometers above the surface, a small height on a planetary scale, not so different from the distance between 2 large cities. High above the clouds and weather, but still well within the Earth-Moon neighborhood, a human-made machine that was destined never to return slipped silently past the world that created it. Most people on the ground had no idea it was there. It was just another quiet object sliding through the dark above the night side, trading Earth's pull for a little more speed. From there, the spacecraft arced outward to Jupiter, the giant that sits as a gatekeeper between the inner and outer solar system. Jupiter's gravity gave Cassini its final big push, a deep tug that lifted it into a path reaching all the way to Saturn. After that, it was mostly empty space and patience. Years of coasting, small corrections from its thrusters, instruments checking in, engineers listening. The distance grew, the sun shrank to a sharper point of light, and Saturn's orbit waited like a ring laid down long before the traveler was born. All the while, Cassini's heart kept humming. Unlike many satellites closer to the sun, it could not rely on solar panels spread like wings to catch light and turn it into electricity. Out where Saturn lives, sunlight is too thin and cold. The power that reaches that distance is only a small fraction of what we receive on Earth. Not nearly enough for a large orbiter with cameras, spectrometers, radio instruments, and a small lander tucked on its side. So the mission used a different kind of warmth, the quiet heat of radioactive decay. Cassini carried 3 radioisotope thermoelectric generators, or RTGs. Inside them were pellets of plutonium, about 33 kilograms in total, carefully prepared and sealed. As the plutonium decayed, it released heat. Thermoelectric materials turned that heat into electricity, without moving parts, without flames or spinning turbines. It's an old, steady technology, especially useful for places where sunlight is scarce or unreliable. Thanks to those RTGs, Cassini could generate hundreds of watts of power, enough to keep its instruments alive and its systems talking, even in the dim reaches around Saturn. Near the end of its life, long after launch, those generators were still producing something like 700 watts, a steady glow of energy in the dark. Of course, putting radioactive material on a spacecraft that swings past Earth is not a decision anyone makes lightly. Engineers and safety experts spent years calculating what would happen in the worst imaginable case. If something had gone terribly wrong, and Cassini had broken apart in our atmosphere during launch or during that close Earth flyby, the plutonium inside could have been scattered and inhaled or ingested by people around the world, spread thinly over the entire planet. The amount was small, but not harmless. In the most pessimistic models, if everything went just wrong, it might have caused on the order of a few thousand additional cancer deaths over many years, numbers that are hard to hold in the mind, because they are both huge and tiny at once, compared to all the other risks people live with. NASA weighed that possibility against the probability. The chance of such a catastrophe was estimated at about 1 in a million. Engineers designed the fuel capsules to survive explosions and re-entry, layered safety systems on top of each other, checked and rechecked the math. In the end, they accepted that slim risk in exchange for what the mission could offer: a deep, long look at a giant planet, its moons, and its rings. Knowledge that would not be possible any other way. It's an uneasy kind of courage to launch something that carries both danger and promise, but it's also part of how exploration has always worked. We measure, we worry, we reduce the risk as much as we can, and then, gently, we let go. The choice of RTGs did more than just solve a power problem. It gave Cassini the chance to live a long life. Solar panels would have struggled so far from the sun, and they would have been heavy and fragile. The generators, by contrast, simply sat and warmed and worked year after year. In fact, even when Cassini's story ended at Saturn, the RTGs themselves could have kept going. They didn't run out. What the spacecraft eventually ran low on was not power, but propellant, the fuel used by its small thrusters to adjust its course and keep its antenna pointed carefully toward Earth. Without that propellant, Cassini would have lost the ability to aim itself or to choose its path. A spacecraft around a planet is never truly still. Gravity tugs at it, nudging its orbit over time. If it had been left alone after its fuel was gone, Cassini would eventually have wandered in ways no one could quite predict, perhaps passing too close to one of Saturn's moons and risking a crash there someday. The mission planners did not want this silent, aging machine, with its traces of earthly material and its unsterilized corners, to tumble into any place that might harbor delicate chemistry or the possibility of life. So they made a different, more deliberate choice for its ending, one that would come later in the story, a controlled dive into the planet itself, where everything it carried would be broken apart and folded into Saturn's own atmosphere. By the time that moment arrived, Cassini had already traveled its billions of kilometers, slipped past Venus, Earth, and Jupiter, and settled into years of quiet companionship with Saturn. Rare alignments and careful calculations had been turned into streams of data and softly glowing images. All of it rested on details that sound almost ordinary when spoken aloud: tens of kilograms of fuel, a few compact power sources, a sequence of gravity assists, but together they became the spine of a journey that let us, in our minds, drift among the rings of a distant world and feel, for a little while, that the outer solar system was not quite so far from home. Out there, far from the bright daytime world, one small part of that spacecraft was waiting in the dark, asleep above a moon that looks like no place on Earth. It was a lander attached to the larger traveler called Cassini, which spent its long years tracing Saturn's rings, wandering past its icy moons, listening to the invisible bubble of magnetism around the planet, and reading the soft layers of its clouds. Among all those tasks, one carried a special kind of tenderness: the work devoted to Titan, Saturn's largest moon, where sunlight turns the sky into a constant golden haze, and where lakes and rivers are not made of water at all. That is where the Huygens probe comes in. Huygens was a small lander, a little more than 1.3 meters across, about the size of a big armchair and weighing around 300 kilograms. It was built and cared for by the European Space Agency, riding quietly on Cassini's side like a passenger tucked against the window. For most of the long voyage it slept, while Cassini handled the flying and the radio calls and the navigation through the deepening cold towards Saturn. Only when the time was right did the two finally separate, each following its own path through the dim light around the ringed planet. When Huygens detached from the main spacecraft, it drifted alone for about 22 days through the stillness near Titan. Almost all of its systems were turned off. Inside, nothing moved except a single, patient wake-up timer, counting down in the dark. No cameras looking out, no radio messages, just a quiet promise that, at the right moment, the probe would open its eyes. The plan was simple and very human. Let it sleep as long as possible, then gently nudge it awake only 15 minutes before it had to face the thin edge of Titan's atmosphere. Outside the shell, the sky of Titan would have been a smoky orange, lit by a distant sun that gives only a fraction of the light we see on Earth. Huygens, following its careful programming, unfolded and prepared for descent. Parachutes opened. Instruments that had waited for years began to breathe in numbers, air pressure, temperature, the makeup of the gases, the tug and swirl of the wind. Everything about this moment had been built for one main purpose: not to drive around, not to last for months, but to fall slowly, patiently, and pay attention on the way down. The descent lasted about 2.5 hours. In that time, the probe gently dropped through layer after layer of Titan's atmosphere, turning the unknown into quiet lines of data. It sampled the air, listening for methane and nitrogen, tracing how the winds pushed and twisted as it fell. It watched the haze thin. It watched the strange landscape below come into view, a world where rivers have carved channels through icy ground, and where liquid hydrocarbons, not water, can pool into lakes and seas. Every minute of that fall was precious because Huygens carried only a limited store of battery power, enough for just a short time after it reached the surface. Scientists on Earth were not even sure what kind of surface was waiting. Titan could have greeted the little lander with a smooth ocean of dark liquid, or a slushy shoreline, or a frozen plain. So Huygens was designed to handle all of these possibilities. Its body was built to float if it splashed down into a lake. Its instruments were ready to taste liquid or dust or ice, whatever met it at the end of its long journey. But when the descent finally ended, Huygens did not land in an ocean. It settled instead onto something that looked very much like the bed of a dried-up lake. The surface around it appeared pebbly and dark, with rounded ice rock shapes scattered across the ground, as if liquid had once flowed there and slowly drained away. The probe touched down, bounced just a little, and then stayed. To the surprise and quiet delight of the teams who had built it, the lander kept working beyond what many had expected, sending back not only atmospheric readings, but also close-up views from Titan's surface itself, a horizon under a heavy orange sky, lit as gently as a sunset that never ends. While all this was happening, Cassini remained in orbit high above, still circling Saturn with patient grace. Its own mission was longer and wider, stretching over 13 years in the Saturn system. During that time, it flew past moon after moon, looked down on storms wider than our whole planet, and tasted the fine spray of ice and vapor coming from tiny Enceladus. With every loop, its cameras gathered an enormous collection of images. Saturn's broad rings slicing across the darkness, delicate ring shadows laid like threads on the cloud tops, and small moons half-lit along the ring plane. From those images, people on Earth later stitched together slow, steady sequences that feel almost like sitting on the spacecraft itself. The views are real. They come from photographs, carefully lined up and gently adjusted in color and brightness, so that motion becomes smooth to our eyes. There is no computer-generated planet here, just what Cassini actually saw as it moved through the Saturnian night. All missions have a limit, though, and eventually, Cassini's fuel for steering and pointing began to run low. The main engines and instruments could still work, but the ability to adjust its path and keep its antenna aimed at Earth would not last forever. The people guiding the spacecraft had to think not only about how to end the mission safely, but also about how to fill those last years with the deepest, richest science they could gather. There was also another, quieter responsibility: to protect the moons that might shelter the ingredients for life, worlds like Enceladus and Titan, from any tiny hitchhiking microbes that might have come from Earth. So a plan was made that was both bold and careful. As the end drew closer, engineers sent new commands to Cassini, asking it to fly routes it had never taken before, routes that would bring it close to the rings and close to the tops of Saturn's clouds. Starting on the 30th of November 2016, the spacecraft climbed high above Saturn's North Pole, then swooped down again to skim just outside the narrow F-ring, that thin, twisty edge of the main ring system. It repeated this rising and diving path 20 times, each orbit giving a slightly different view of the rings, the planet, and the space in between. Cassini threaded its way through regions crowded with small, icy particles, while always keeping itself safe enough to send data home. From this perch just beyond the rings, it could see structures and waves inside the ring system in greater detail than ever before. It could also watch how the rings cast shadows on Saturn's atmosphere, tracing how light and darkness played across the clouds as the seasons slowly shifted in the distant outer solar system. Then, on the 22nd of April 2017, Cassini was sent on a new path that would carry it even closer to Saturn than any spacecraft had ever gone. This was the beginning of what came to be called its grand finale, a series of daring dives between the inner edge of the rings and the top of Saturn's atmosphere. Instead of staying comfortably outside the ring system, Cassini would now leap over the rings and plunge through the narrow gap between the rings and the planet itself, over and over again. Each orbit took it through this gap at great speed, skimming a region no mission had ever explored before. During these dives, Cassini turned its whole body into an instrument. By carefully tracking how the spacecraft sped up, slowed down, or was tugged off course, scientists could map Saturn's gravity field in fine detail, learning how mass is arranged inside the planet. The magnetometers measured the shape and strength of Saturn's magnetic field, seeking hints about how deep the winds might reach and how fast the hidden interior is really rotating. Other instruments listened for tiny charged particles and dust grains, counting how ring material is slowly raining down along the planet's magnetic field lines into the upper atmosphere. Its cameras, too, were watching. From this close vantage point, Cassini could see the rings not as a single flat band, but as a finely layered structure, full of gaps, clumps, and gentle waves stirred by the pull of nearby moons. It could look down on cloud patterns that had only ever been glimpsed from afar, subtle swirls and bands, storm systems shaped by winds that circle the planet in long, unbroken streams. The images from these orbits have an intimate feeling, as if the spacecraft is almost brushing Saturn's veiled surface, close enough to watch the play of light across the tops of the clouds. The information gathered in this unique region helped refine our picture of how giant planets form and change. By improving estimates of how much material is locked up in the rings, the spacecraft brought scientists a little closer to answering long-standing questions. Are the rings ancient, left over from the time when Saturn itself was young? Or are they younger, perhaps born from a shattered moon or captured comet? How quickly are they losing material into the planet below, and how long might they last? All of this knowledge came with a cost that had been accepted from the beginning. To protect the possibility of life on moons like Enceladus and Titan, Cassini could not simply be left drifting when control was no longer certain. There was always the chance that, far in the future, a powerless spacecraft might wander and eventually collide with one of these fragile, interesting worlds, carrying Earth's microbes with it. So the final orbits of the grand finale were shaped not only by curiosity, but by a kind of planetary kindness, a promise not to disturb places that could, in some distant era, harbor life. On its last orbit, Cassini aimed its antenna at Earth one more time and dipped into Saturn's upper atmosphere. As it sank into the thickening air, the spacecraft kept transmitting for as long as it could, sampling the gases it flew through, sensing the magnetic and electric fields, feeling how the atmosphere tugged at its motion. Friction slowly heated its body, the way a meteor flares in Earth's sky. Bit by bit, the signal weakened, then slipped away not with a dramatic crash, but as a steady fading into the background noise of space. With that final plunge, Cassini's nearly 20 years of journey and work came to an end. From launch near Earth to dissolution in Saturn's clouds, It left behind no wreckage on any moon, only data, images, and a quieter, truer sense of what a ringed giant planet is really like. After spending its last breath, reaching for a little more knowledge, and then giving itself back to the world it had studied for so long. Long before that last orbit, NASA had to make a quiet kind of bargain with Cassini. The spacecraft could have lived a little longer in a safe, distant track, or it could spend its remaining strength on a final, intimate approach to Saturn, slipping into places no machine had ever gone before. By the time that choice arose, the ending was already written into its tanks. Cassini's fuel was running low, and a long future was no longer possible. So the decision became simple in a gentle, bittersweet way. Rather than let it fade along a far-off path, the teams on Earth chose to send it inward, trading longevity for closeness, safety for one last sweep through Saturn's hidden spaces. That choice opened the door to a whole new view of Saturn's neighborhood. With careful commands, Cassini was allowed to dive through the spaces near the rings and skim close to tiny moons that spend their lives shepherding ring particles into delicate shapes. From this perspective, all the subtle details that had once been just hints in the data became clearer, almost like moving your chair closer to a window and suddenly seeing the fine weave in the fabric of a curtain. One of the small worlds Cassini met in this way is Atlas, a moon only about 40 kilometers across. It moves along the outer edge of Saturn's bright A ring, drifting like a tiny boat at the boundary of a shining river. In close-up images, Atlas looks strangely gentle and smooth, almost like a soft pebble brushed by water for a very long time. You would expect a moon to be pitted with impact craters, scarred by long-ago collisions. But Atlas is not. Its surface seems oddly clean, wrapped by a wide ridge around its equator that gives it a shape almost like a little flying saucer or a pressed dumpling. This soft outline is not an illusion. Dust and ice particles from the nearby rings slowly settle onto Atlas, especially around its middle, building up a blanket of material over time. The moon's gravity, though small, is enough to hold on to this falling ring snow. Little by little, the ridge grows, smoothing out older scars and covering rough places. When you look at it in Cassini's images, it feels as though the moon is being quietly tucked in by Saturn's rings, wrapped in the fine dust that forever drifts past. Something similar happens with another small moon called Pan. Pan is smaller than Atlas, about 30 kilometers wide, and it lives in a narrow gap in the rings known as the Encke Gap. You can imagine Pan as a tiny, steady sweeper moving along its orbital track. Any loose ring particles that wander into that narrow corridor do not just stay there. They are gently gathered by Pan's gravity, collected as it goes. This constant sweeping helps keep the gap open and well-defined, a clear lane through the bright ring material. Over time, Pan too has gathered a smooth, equatorial ridge, wearing the dust and ice of the rings like a soft collar. Even tinier moons play a part in shaping the rings. One of them, a small body only about 8 kilometers across, travels in a very narrow gap in the A-ring. Its gravity is weak, but not zero. As it moves along its path, it tugs at the nearby ring particles, stirring them into ripples that extend for hundreds of kilometers. In some images, you can see a narrow, delicate wake trailing behind the moon's path, like the line left on the surface of a lake when a boat has passed. Those ripples in the rings do not just spread sideways, they can also rise and fall, lifting parts of the ring plane gently above and below the average level. When the sun sits low over the ring system, these vertical waves cast long shadows across the bright ice, making the ripples feel almost like frozen waves on a sea. If you imagine yourself sitting on that little shepherd moon, watching the ring particles dance in the light, Saturn hanging huge and pale in the background with its other moons drifting by, the scene feels both quiet and deeply alive. The rings themselves became a kind of canvas for Cassini's close-up work during the grand finale. From these new trajectories, the spacecraft could glimpse patterns that are easy to miss from far away. One particularly striking pattern is something called a spiral density wave, and Cassini captured one of the most beautiful examples in the region of the B ring, influenced by the moon Janus. The image, at first glance, looks like a series of many separate rings, tightly packed and slightly curved, like the grooves on a very fine record. But the pattern is more subtle than that. What seems to be many distinct rings is actually just two spiral arms, wrapped again and again around Saturn. Each arm loops around the planet many times, so every second bright band you see in the image belongs to the same spiral. The wave is created by an orbital resonance, a kind of steady gravitational rhythm between the ring particles and the moon Janus. At that particular location, the particles go around Saturn twice for every single orbit Janus completes. And this repeating tug gently bunches the particles into a spiral pattern. The photograph gives the impression that the whole structure is tilted away at the top left, as though the rings are slanting downward. That is just an illusion. The tilt you think you see comes from the way the spacing between the wave crests changes with distance. Near the resonance, the ripples are farther apart. As you move away, the wavelength shrinks and the bright lines appear more tightly packed. The result is a pattern that tricks the eye into reading a tilt where there is none, like looking at a carefully drawn optical illusion. What makes this wave even more quietly astonishing is that it holds a kind of memory. Janus does not always stay at the same distance from Saturn. Every few years, it exchanges orbits with a nearby moon named Epimetheus. The two moons share a delicate arrangement where they swap positions roughly every 4 years, trading the inner and outer tracks in a slow celestial dance. Each time this switch happens, the resonance in the rings adjusts slightly, and the wave responds by creating a new crest. Over time, as these crests travel outward from the resonance location, they preserve a record of those orbital swaps. The distance between one crest and the next can be linked to about 4 years of motion. That means the pattern Cassini saw is not just a static structure, it is a timeline written into ice and dust. Parts of the wave near one edge of the image correspond to more recent positions of Janus and Epimetheus, while the more distant portions remember earlier configurations. According to the way scientists interpret the pattern, the farthest part of the wave at the edge of Cassini's view reaches back many decades. It may even encode the positions of Janus and Epimetheus from the era when another spacecraft, Voyager, first flew through the Saturn system in the early 1980 seconds and proved that these two moons are separate bodies rather than one object. In that sense, the rings themselves carry a subtle memory of past visitors and past arrangements, like a diary that nobody wrote by hand, but that exists all the same. Thinking about this can feel a bit like looking at the rings inside the trunk of a tree. When you cut across the wood, you see circular bands that quietly count the years the tree has lived, each ring marking a season of growth. In Saturn's B ring, the spiral density wave becomes a different kind of record, not of rain and sunlight, but of gravitational dances and orbital exchanges. Cassini's images invite you to read that record, to trace the slow story of Janus and Epimetheus as it is gently carved into patterns of ice. All of this unfolds in silence, in a place where no wind blows that a human ear could hear, and no sound carries the way it does in Earth's air. Yet the motion is constant and graceful. Dust grains collide and settle. Tiny moons sweep their paths clean. Waves travel outward, keeping time with moons that swap orbits like partners in a long, slow waltz. Cassini's grand finale gave us the chance to see these subtle motions up close, not as abstract lines on a graph, but as real, textured structures lit by the distant Sunday. As you picture these scenes, you might imagine the spacecraft itself gliding through the darkness just above the rings, its instruments calmly watching, while all around it, shepherd moons, waves, and spirals continue their quiet work. Saturn turns, the rings whisper in ice, the moons keep guiding and shaping. And somewhere within that gentle clockwork, a record of time lies folded into the patterns themselves, waiting for any passing observer to unfold it with patient eyes. If you were to drift there with it, weightless and unhurried, you wouldn't feel the pull of the resonance or the gentle gathering of dust, but you could watch their traces written everywhere you look. The narrow gaps, the softened shapes of Atlas and Pan, the ripples that rise like sighs from a small moon's passing, the spirals wrapping again and again around the planet, they are all quiet answers to the same invisible questions of gravity and motion. Cassini's closeness in those final orbits was like leaning in to listen more carefully, catching details that are always there, but usually too fine and too slow for distant eyes. And when you let that picture settle in your mind, you can carry it back with you into ordinary life. The thought that even in far-off places where no human has ever stood, there are stories unfolding in slow patterns, kept faithfully by dust and ice. Nothing in those rings knows it is being watched or measured, yet still, without hurry, it holds its shape and its history, waiting for any passing observer to notice. In that same deep quiet around Saturn, even the smallest marks in the rings can tell a story. As Cassini threaded those last close paths, it did more than gaze at the broad, familiar bands of ice it came near, enough to see tiny disturbances, delicate patterns that look almost like scratches in frost. Among the most curious of these are little shapes that resemble propellers, scattered here and there in certain parts of the rings, the signatures of hidden moonlets, too small to see directly, and yet large enough to stir the particles around them. To study these gentle scars, scientists often looked at both sides of the ring plane. They compared images of the sunlit face of the rings with images of the shadowed, unlit side, knowing that subtle structures sometimes stand out better against darkness than against light. Even at a scale where each pixel covers about 500 meters, the moonlet itself may be almost invisible, just a faint dot. What stands out more clearly is the pattern spreading from it. A band of disturbed material, stretching forward and backward along the orbit, like the blades of a tiny propeller stamped into the ring. These features arise because a small object, buried in the thin plane of icy debris, tugs on the nearby particles as it passes. Inside its orbit, particles move a little faster, outside, a little slower. Under the moonlet's pull, some are shifted inward, some outward, leaving behind a pair of curved gaps and overdensities that twist with the flow of the ring. Cassini's close views revealed not just one such propeller, but many, some of them near the Encke Gap, some in neighboring regions, each marking the presence of a body no more than a couple of kilometers across. None of these moonlets are thought to be dense, rocky worlds. They may have the consistency of packed snowballs, fragile in some ways, and yet persistent. Embedded in the ring material, they try to carve out lanes as they orbit, but the surrounding particles constantly drift back in, so the gaps never grow into wide corridors like the larger ring divisions made by bigger moons. Instead, the moonlets remain half-hidden, wrapped in their own handiwork, leaving behind only these delicate propeller shapes as evidence that they are there at all. In the faint outer regions, near Saturn's E-ring, Cassini also spotted extremely small but apparently solid clumps of material. They seem to have gathered and hardened around disturbances likely caused by nearby shepherd moons. Unlike the fine mist of particles that can be easily blown apart, these objects have survived repeated passages through the ring, crashing into the more tenuous material without being erased. Each impact kicks out fresh dust, forming hazy halos that follow their orbits. The cores themselves remain hidden inside that haze, too small and too obscured to be seen directly, but their presence is betrayed by the way the light scatters around them. All of this ring activity circled a planet that, during Cassini's final seasons, was tilted so that its northern hemisphere basked in full summer. Around Saturn's North Pole, a remarkable, long-lived pattern stood in clear view, a massive hexagon, a six-sided jet stream wrapping the pole like a slowly turning crown. At its center lay a deep, permanent, polar vortex, a storm with the structure of a huge hurricane, complete with an eye and towering walls of cloud. Seen from above, the shape is so geometric it looks almost designed, straight edges drawn into gas. Over the years, Cassini watched that region change color with Saturn's slow seasons. In earlier images, taken around 2012, the pole appeared darker, more muted. Later, as sunlight bathed the area more directly, the hues shifted and brightened. With the help of different wavelengths of light, scientists traced additional storms dotted across the planet, faint bands and swirls reminiscent of Jupiter's stripes, but softer and less vivid when seen in natural light. The spacecraft's closeness also offered a new kind of intimacy with Saturn's horizon. In some images, the edge of the planet curves gently across the frame, and along one side you can see a thin, diffuse haze in the stratosphere, a glowing layer that fades as your eye moves toward the other side. Cassini's controllers knew that when the spacecraft finally dipped into Saturn's atmosphere, it would not survive long enough to cruise through those upper hazes and look back. The final plunge would be swift and fierce, and the data it gathered would be taken in a brief rush, burned into memory, and transmitted in real time as the spacecraft fell. In the week before that last descent, though, Cassini was still fully alive, turning, pointing, and capturing images. From these final days came a series of time-lapse sequences carefully assembled from individual photographs that let us sense how the system moves, as if you were sitting beside the spacecraft, watching time gently speed up. One of these sequences, from the 8th of September, 2017, lingers on the moon, Enceladus. Throughout its mission, Cassini had treated Enceladus as a special focus, because beneath its bright, frozen crust lies a global subsurface ocean that may hold the ingredients for life. Near its south pole, the surface is fractured into long, tiger-striped fissures. From these cracks, more than 100 water-rich plumes erupt into space, spraying vapor and icy grains outward in ghostly jets. In the cold vacuum, the water instantly freezes, and much of it drifts outward to help form Saturn's E-ring, a wide, diffuse halo of tiny particles. The E-ring itself is so tenuous that it is almost invisible unless the geometry is just right. When it is backlit by the sun, though, it reveals a faint, bluish glow. Cassini's vantage point allowed it to see how Enceladus is constantly feeding and stirring this ring. its plumes disturbing the densest regions and replenishing the supply of fresh ice. In one of the last looks Cassini had at those plumes, captured over a span of about 14 hours, you can watch Enceladus turning slowly as the jets rise and fall in brightness, like breath in the cold. Around the same time, when Cassini was near the farthest point of its final orbit, it turned its cameras towards Saturn and the main ring system to create a wide mosaic in natural light. In that view, you can see the thickest rings, the D, C, B, A, and the narrow F ring laid out in graceful arcs, with Saturn's short shadow cast across them. Because it was northern summer, the planet's famous hexagon storm sat in clear sunlight at the top of the globe. Along the planet's disk, subtle bands emerge, softly striped even in ordinary light. One gentle detail in that mosaic is the way Saturn's night side refuses to be completely dark. Where you might expect to see a simple black silhouette, the unlit hemisphere is instead faintly washed with a dim glow. That light does not come from the sun directly, but from the rings themselves. Sunlight bounces off the bright ring particles and falls back onto the planet's night side, lighting it the way snow can brighten a winter evening. Beneath that ring glow, lower in the atmosphere and away from the reflected light, Saturn sinks into deep darkness. As Cassini continued along its path, on September 12 it once again brought its gaze close to the atmosphere, near the planet's terminator, the line dividing day from night. When the sun is low over those cloud tops, long shadows stretch across the scene, and structures that normally blend together suddenly stand out. In these images, tall cloud formations cast dark streaks that run for many kilometers, outlining their shapes in relief. The region in view is about 5,500 kilometers across, wide enough for Saturn's large moon Titan to fit within it. Each day that week, Cassini's orbit carried it closer. On September 13, one of the small moons in the ring system, Daphnis, a tiny body that lives in the Keeler Gap, appeared once more in the spacecraft's field of view. In the images, you can see delicate ripples in the rings both in front of the moon and trailing behind it. These waves arise because the inner ring particles move faster than Daphnis and overtake it, while the outer ring particles move more slowly and lag behind. As particles rush past, the moon's gravity pulls on them, creating raised waves that briefly disturb the smooth ring plane. By the time the ring material on either side has moved away from the moon's orbit, those waves gradually smooth out, leaving only the memory of their passage stamped into the pattern for a while. Watching the sequence, you can almost imagine tracing the path of each particle as it feels a tiny tug, rises slightly above or below the ring plane, and then settles back into its place. Later that same day, Cassini turned its attention outward across the system for one more gentle survey. It captured another view of Titan, the large, hazy moon it had studied so often, a world with a thick nitrogen atmosphere and lakes of liquid hydrocarbons resting on its frozen surface. In the image, Titan appears as a softly glowing orb beyond the rings, its outline blurred by the dense air that wraps it. Cassini also took in a final look at the uneven F ring, with its knotted structure barely visible near the edge of the frame, hinting at the restless interactions of small shepherd moons and clumps within it. As Saturn grew larger in the cameras in the final approach, the spacecraft took a last lingering gaze at Enceladus. Over about 40 minutes, it watched the moon move across the sky until it slipped behind the limb of Saturn, disappearing from view. The plumes that had once been a central mystery were now familiar, but seeing them vanish behind the curve of the planet carried a special weight, knowing that there would be no more return visits. The final image Cassini ever took shows the area of Saturn where it would soon dive to its end. It is night there, so the scene is not lit by the sun directly. Instead, once again, the rings act as a faint mirror, scattering enough light onto the atmosphere to outline the region. In that picture, you can sense the quiet before the plunge, as if the spacecraft were looking at the place it would soon become a part of. After that, there were no more images. On the last day, every bit of available bandwidth was reserved for data about the atmosphere itself. In those final moments, measurements were more precious than pictures. This was a chance unlike any we had ever had, to sample Saturn's atmosphere from the inside, even briefly. When Cassini first touched the thin outer layers, it was traveling at about 123,000 kilometers per hour, skimming just about 1,900 kilometers above the tops of the visible clouds. The atmosphere at that height is still very tenuous, but at such speeds, even thin air exerts a powerful force. The spacecraft used the last of its fuel in small thrusters to keep its large antenna pointed toward Earth, fighting the tendency to tumble. For a short while, it worked. Cassini's instruments tasted the gases rushing past and sent their readings home in a steady stream, telling us about the composition and behavior of Saturn's upper atmosphere. A minute later, though, the air had grown thicker, and the thrusters had to push harder and harder to keep the spacecraft stable. They eventually reached their maximum effort, firing continuously. The atmosphere pushed back. 10 seconds or so after that point, the force of the airflow finally overcame Cassini's ability to maintain its orientation. The spacecraft began to spin, its antenna slipping away from its tight lock on Earth. As the radio link broke, the data stream faded and then vanished, leaving the ground receivers listening only to the background hiss of space. Inside Cassini's computers, if they had had the time, routines would have been trying to understand what was happening. Gyroscopes and star trackers would have reported that the spacecraft was tumbling, and the software would have tried to enter a safe mode, shutting down non-essential systems, redirecting power, attempting to steady the spin. But there was no longer enough time or control for such recovery. Within about a minute of losing contact, the increasing heat and mechanical stress tore the spacecraft apart. Pieces of metal, insulation, and equipment broke away, each fragment rapidly heating, glowing, and then vaporizing in the high-altitude layers of Saturn's atmosphere. In a short span of time, everything that had once been the Cassini spacecraft was converted into a thin smear of gas and plasma, indistinguishable from the planet's own material. From Saturn's point of view, a small, human-made object entered its sky and burned up, adding a trace of new atoms to the air. From our point of view, though, a 20-year journey had ended in the only way it could, not with a sudden silence, but with one last flood of information, followed by a gentle, inevitable fading. Cassini left no monument on any moon, no relic on the surface to mark its passing. Its legacy is stored instead in the patterns it revealed: the propellers in the rings, the waves around tiny moons, the whisper of the E-ring, the bright hexagon at the pole, and the hidden structure of Saturn's atmosphere itself. On a quiet night, you can think of that final dive as a kind of homecoming. A spacecraft built on Earth, launched from our world's surface, traveled across the solar system, and spent years circling a distant giant. In the end, it did not simply stop. It returned its last secrets, and then joined the planet it had studied, becoming part of the clouds it once observed from afar. All that remains for us is to remember that even far from home, under pale sunlight and surrounded by rings of ice, something built by human hands once flew, watched, and, in its own silent way, said goodbye. When Cassini's final signal faded into the background noise of space, the story of the spacecraft itself was over, but the story hidden in its data was only beginning. That last stream of information, sent as the probe fell into Saturn's atmosphere, took about an hour and a half to cross the darkness and reach Earth. In a quiet room full of listening antennas, the final measurements arrived. Samples of Saturn's upper air, readings from its ionosphere, traces of tiny dust grains, and the last careful numbers describing the planet's magnetic field. Once the engineers were sure the transmission had come through cleanly, there was a gentle certainty. The last part of the mission had worked. Cassini had done what it was built to do, right up to the moment it burned away. Those final readings slid into a vast archive, alongside years of earlier observations of rings, moons, fields, and clouds. This is one of the quiet wonders of a mission like Cassini. The hardware ends, but the data keeps unfolding. Scientists around the world still sift through those records, comparing them with each other, combining them with new models, and looking again with fresh questions. Some results are small adjustments, gentle corrections to the picture we thought we had. Others reveal something more unsettling, that Saturn, a planet we thought we understood fairly well, is in many ways stranger than we imagined. From a distance, Saturn seems almost familiar. Its rings are iconic, the widest and brightest in the solar system. Its hazy, yellow cream disk is instantly recognizable, a soft, blurred lantern against the dark. It is the second largest planet, the least dense, and the sixth major world from the Sunday. Those are simple facts, easy to list. They can give the impression that Saturn is mostly understood, a known entry in the catalog of worlds. Yet beneath those calm statistics lies a more puzzling truth. Cassini's measurements revealed that there is a deep mystery under Saturn's obscuring atmosphere, one that scientists still have not fully untangled. The planet behaves in ways that do not fit comfortably within our usual models. Its temperature, its magnetic field, and even the length of its day refuse to line up as neatly as we would like. Saturn is, in many respects, an unsolved riddle, wearing a very familiar face. Cassini arrived at this riddle on the 1st of July 2004. It was not the first visitor. Earlier, Pioneer 11 and both Voyager probes had brushed past Saturn on fast one-time flybys. They gave us our first close looks at the rings and moons, then continued outward. Cassini, by contrast, stayed. For 13 years it moved in looping paths around the planet, changing its orbit again and again to sample different angles and distances. On board, sensitive instruments watched in many kinds of light, sniffed the composition of gases, and felt the tug and shape of invisible magnetic fields. Some of what Cassini found fit neatly with expectations, but other discoveries only made the planet more mysterious. One of the most striking puzzles sits over the North Pole, a vast hexagon-shaped storm. This feature, about 29,000 kilometers across, is a jet stream wrapped into a six-sided figure. Each of its straight edges is long enough to fit the Earth comfortably inside. Unlike the more ordinary cloud bands that sweep around Saturn, pushed by winds of up to roughly 1,800 kilometers per hour, the hexagon does not drift in longitude. It turns with the planet, as if it were painted onto the spinning globe. On Earth, scientists have recreated smaller hexagon-like shapes in swirling fluids, showing that such patterns can emerge naturally under the right conditions. But no laboratory setup matches the scale, sharpness, and persistence of Saturn's polar hexagon. It remains a strange, geometric landmark in an atmosphere otherwise full of flowing curves. And the hexagon is only one piece of the broader puzzle. As researchers worked through the huge store of Cassini data in the years after the mission ended, other questions emerged. One of them sounds simple at first. How long is a day on Saturn? On a solid planet, you can answer that by tracking fixed surface features. You watch a continent or a crater rotate into and out of view and count the hours. Saturn offers no such convenience. Whatever solid or liquid core lies beneath, it is hidden under a deep, thick blanket of cloud. The visible atmosphere moves at different speeds, at different latitudes and depths. Fast jet streams race along, cloud bands slide past each other, and storms drift. Those motions do not necessarily match the rotation rate of the deep interior. The rings do not help with this question either. Each particle of ice or dust orbits Saturn at a speed set mostly by gravity and its distance from the planet. Inner parts of the ring system move faster, outer parts slower. That motion is not locked to the underlying spin of Saturn's core, so it cannot act as a reliable clock for the planet as a whole. For other giant planets, scientists often use a different approach. They measure the planet's magnetic field instead of its clouds. Many worlds, including Earth and Jupiter, generate their magnetic fields through a dynamo process. Deep inside, electrically conducting material moves and churns as the planet rotates, creating currents that give rise to a large-scale magnetic field. A typical feature of such dynamos is that the magnetic poles are not perfectly aligned with the planet's spin axis. The tilt means that as the planet rotates, the magnetic field appears to wobble, sweeping around like a lighthouse beam. If you sit in space with a suitable instrument and watch this wobble, you can time how long it takes to make a full cycle. That period usually matches the rotation of the deep interior. It is a powerful way to measure the length of a day on a world where you cannot see the surface. Saturn, however, stubbornly refuses to cooperate. Cassini's measurements showed that Saturn's magnetic field is astonishingly well aligned with the planet's rotation axis. The difference between the two appears to be less than 1/10 of a degree. As far as we can tell, the field does not wobble in the way our dynamo theories say it should. According to those models, a field so perfectly aligned ought to fade away quickly, yet Saturn's field is strong, steady, and long-lived. In terms of overall strength, Saturn's magnetic moment is about 580 times greater than Earth's. It carves out a large bubble in space around the planet, shapes the paths of charged particles, and influences the environment through which the rings and moons move. Clearly, something deep inside Saturn is generating a powerful magnetic field. Just as clearly, the way that field appears on the outside does not fit comfortably into our usual expectations. No one has a final answer yet. One possibility is that the basic dynamo in Saturn's interior behaves much like others, but that higher layers, perhaps a special, electrically conducting region in the atmosphere, smooth and reshape the field until it looks nearly perfectly aligned from our vantage point. Another is that Saturn is using a variation of the dynamo process that our current models do not yet capture. In either case, the magnetic field does not give us the handy rotational tick that it does for other planets. So scientists turn to another kind of signal, radio waves. Saturn is an electrically active world. Charged particles move through its atmosphere, along its magnetic field lines, and even between its rings and its upper layers of gas. These charged motions produce radio emissions, bursts of energy at wavelengths too long for our eyes, but easy for radio instruments to detect. Early observations showed that the intensity of these waves rose and fell in a roughly regular pattern. Stronger bursts appeared about every 11 hours or so. From the Voyager flybys, scientists used this pattern to derive a first estimate of Saturn's day. The number they settled on was 10 hours, 39 minutes, and 23 seconds. It was widely accepted as the best measure available. When Cassini arrived, there was hope that its longer, closer view would tighten this figure even further, perhaps adjusting it slightly and reducing the uncertainty. At first, Cassini's data seemed to support the earlier estimate, but as the mission went on and more years of radio measurements were collected, something curious became clear. The period between peaks in the radio waves was not fixed. It drifted over time by about 1% over the course of a year, sometimes lengthening and sometimes shortening. It was as though Saturn's radio clock were slowly and gently sliding back and forth. If you interpreted that drift as a true change in Saturn's rotation, you would have to conclude that this huge planet was sometimes speeding up and sometimes slowing down its spin. For a world as massive as Saturn, that is essentially impossible on such short timescales. Nothing we know about in its neighborhood could apply the necessary torque to change its rotation that way. The more reasonable conclusion is that the radio waves are not tracing the deep interior directly. Instead, they are being influenced by something higher up. The best current picture is that Saturn's radio emissions are shaped by complex electrical and magnetic processes in its outer atmosphere and magnetosphere. Winds, currents, and charged particles in those layers can shift the regions where radio waves are produced, changing the apparent period of the signal. Over months and years, as those patterns evolve, the day length, measured by radio waves, drifts, even though the solid and liquid interior beneath is likely rotating at a steady, unhurried rate. Saturn's auroras offer another hint that its electrical environment is unusual. On Earth, the northern and southern lights arise mainly from charged particles carried by the solar wind. When those particles follow magnetic field lines into our upper atmosphere and collide with atoms there, they create shimmering curtains of green and red. Saturn's poles also glow with auroras, but Cassini found that at least some of them brighten and fade without any matching change in the solar wind. They seem to be driven, at least in part, by processes within Saturn's own system. Those processes likely involve the planet's rings and moons. Material from the rings and from moons like Enceladus can become ionized, turned into charged particles, and then guided by Saturn's magnetic field down toward the poles. When they strike the upper atmosphere, they not only make light, they also deposit heat. Parts of Saturn's high-latitude atmosphere are warmed far beyond what sunlight alone would provide. That extra warmth adds to Saturn's larger energy budget. When you total up how much energy the planet emits into space, it is roughly twice as much as it receives from the Sunday. Some of that surplus can be explained by the slow gravitational contraction of this giant world. Over time, Saturn's own weight squeezes it, and the compression releases heat from its interior. But Cassini's measurements showed that this is not the whole story. There are deeper processes at work. To picture them, imagine descending through Saturn's atmosphere. The planet is made mostly of hydrogen and helium. Near the top, they exist as familiar gases, drifting in broad, layered winds. As you go deeper, the pressure builds. Eventually, hydrogen is squeezed into a liquid, and deeper still, into a metallic form that conducts electricity. In these depths, some scientists think droplets of helium may separate out from the mixture and rain downward, releasing heat as they sink. There are even ideas about carbon-forming crystals in certain layers, creating diamond rain that falls slowly toward the interior, adding frictional warmth as it goes. Higher up, where the auroras shine, the added heat from incoming particles creates regions of hot, thin air. Where these hot zones meet cooler surroundings, strong winds can form. These winds do not just move neutral gas. They can also carry charged particles, turning large swaths of the atmosphere into moving electrical currents. Saturn's upper layers may host powerful, electrically charged winds, flowing around the planet like rivers of air and current intertwined. Those moving charges can generate their own magnetic effects. If there is a particularly conductive layer within Saturn's clouds, moving at a different speed from the layers above or below, it could distort the overall magnetic field seen outside the planet. It might smooth out the irregularities that would otherwise produce a clear wobble, making the field appear more perfectly aligned with the spin axis. The same flows could shift the zones where radio emissions are strongest, producing the drifting day length that Cassini measured. None of this is settled yet. The explanations are still being tested, adjusted, and debated. But taken together, they offer a glimpse of Saturn as a far more dynamic and layered world than its soft appearance suggests. Under that pale, hazy glow, hydrogen is being pressed into exotic states. Helium may be raining like a slow, silent storm, and charged winds may be wrapping the planet in invisible bands of current and magnetism. Cassini did not solve these mysteries once and for all. Instead, it traced their outlines and handed us the puzzle with finer detail. Its measurements of Saturn's atmosphere, radiation, auroras, and magnetic field gave us the first real hints of just how complex this giant planet truly is. Now, with the spacecraft gone, what remains is an invitation to keep coming back to the data, to keep refining our models, and to accept that Saturn, for all its familiar beauty, is still a place where the rules are more intricate than we yet understand. Even after Cassini's last whisper of data was received and stored, many of the explanations built from it still feel like sketches rather than finished paintings. The broad shapes are there, the outlines are clear enough to follow, but the details are still soft at the edges. Scientists continue to move patiently through the archives Cassini left behind, rechecking measurements, comparing different years and viewing angles, looking for patterns that might tighten a loose idea into something firmer. If those answers do not appear in the existing data, then one day another spacecraft will have to return to Saturn and sink its instruments into the same mysteries again. For now, much of Saturn remains a set of open questions. Its heat, its magnetic field, the strange behavior of its auroras and upper winds, even the way its interior is layered, none of these yet come with a final, tidy explanation. But at least one of the big puzzles that bothered scientists for decades has found a calm solution: the true length of Saturn's day. And surprisingly, the final clue really did lie in the rings after all, just not in the way people had first expected. Earlier, attention had focused on how Saturn's magnetic field and electrical environment might influence the rings. This time, the thinking reversed. Instead of asking how the planet's fields affect the rings, scientists asked how Saturn's own shape might tug on them through gravity. Saturn is not a perfect sphere. It is slightly squashed at the poles and bulged at the equator, shaped by its rapid rotation. Any subtle irregularities in that shape change the way its gravity pulls at nearby material. The rings, spread out in a wide, thin disk, became the perfect sheet on which Saturn could write those gravitational fingerprints. Where the pull rises and falls just right, the planet's interior can send a kind of shiver through the rings, creating gentle ripples in the distribution of particles. These waves are not produced by moons or outside forces, but by vibrations inside Saturn itself, echoing outward through gravity. By carefully mapping the locations of these ripples and measuring the distances between them, scientists could work backward to find the frequency of the internal motions that created them. That frequency, in turn, is tied to the rotation of the deep interior. It was a quiet kind of seismology, but instead of listening to earthquakes on a crust, researchers were reading the faint quivers of a gas giant in the patterns of its rings. When the calculations were done, the answer that emerged was precise and steady. A Saturnian day appears to last 10 hours, 33 minutes, and 38 seconds. This time, the number is not drawn from drifting radio signals or from clouds that ride the winds. It comes from the way the planet's mass itself moves and pulls, written into the structure of the rings like a signature. There is still room for tiny refinements, but most researchers now feel quietly confident that this figure is very close to the true rotation period of Saturn's interior. One major question, at least, has eased into focus. The rest, however, still wait. The strange alignment of the magnetic field, the extra heat, the complex auroras and charged winds, those are pieces of a larger puzzle that may need new eyes and new instruments to solve. The next time humanity sends a mission to the Saturn system, it will not be aimed at the planet itself, but at one of its most intriguing moons. In 2027, if all goes according to plan, NASA's Dragonfly spacecraft will launch toward Titan, Saturn's largest moon and one of the most Earth-like places we know beyond our own world. Titan has a thick atmosphere dominated by nitrogen, just as Earth's does, but almost entirely without oxygen. The air is so dense and cold that methane, which is a gas in our skies, can act like water does here. On Titan, methane can condense into clouds, fall as rain, and gather into lakes and seas that pool in low-lying basins. Rivers carve channels through the icy crust, carrying liquid hydrocarbons the way streams on Earth carry water. The surface is shaped by weather and seasons, with dunes and shorelines and fog, all under a soft orange sky. It is a world both familiar and alien, echoing Earth's cycles in slower, stranger forms. Dragonfly will not orbit Titan from afar. It is designed to fly within its sky, a rotorcraft that can lift off, travel across the landscape, and land again in new locations. It will sample the surface, taste the atmosphere, and look for complex organic molecules that might hint at chemistry on the path toward life. Titan's thick air and low gravity make it an unusually gentle place for such a flying vehicle, and its rich organic chemistry turns it into a laboratory for questions about how life might begin. While Dragonfly's focus will be Titan rather than Saturn itself, every new piece of information from the Moon adds to the broader picture of the Saturn system. Titan's atmosphere, its methane lakes, its interaction with Saturn's magnetic field and radiation, all of these are threads woven into the same fabric. Still, it may be a long time before a mission is sent specifically to probe Saturn's interior, its deep atmosphere, and its magnetic engine again. The unanswered questions may have to wait patiently in the dark. In the meantime, Saturn continues its slow breathing. Winds whirl, clouds rise and sink, and the balance of gravity and magnetism guides the rings and moons. Charged particles flow along its magnetic field lines. The planet's presence shapes the space around it, keeping the rings confined to their thin, bright plane. One of the more surprising messages from Cassini's data is that the rings themselves may be much younger than Saturn. The planet is over 4 billion years old, formed in the early days of the solar system when the sun was still new and the other planets were taking shape. The rings, however, show signs of being perhaps only on the order of 100 million years old, maybe even younger. For cosmic time, that is almost recent, a structure that may have formed long after the original birth of the planet. There are different ideas about how they appeared. Perhaps a moon wandered too close and was torn apart by Saturn's gravity, its icy body shredded into countless pieces. Perhaps a large comet or icy object broke apart in the planet's grip, seeding a new ring system. Whatever their origin, the current rings are not frozen in place. Cassini's measurements suggest that ring material is slowly spiraling inward, raining down along Saturn's magnetic field lines into the upper atmosphere like a fine, invisible drizzle. If those estimates are correct, the rings may fade significantly over the next 100 million years or so, thinning and darkening until they are no longer the brilliant, sharp-edged structures we see today. One day, far in the future by human standards, but not unimaginably far in the life of the solar system, Saturn may be left with only faint, ghostly remnants of its once splendid rings, or none at all. The planet will still be there, still complex and enigmatic, but that bright, iconic feature will have passed. There is a soft sadness in that thought, the idea that we live in a moment when Saturn wears its rings at full brightness, and that future beings, if any, are watching, might see a plainer world. At the same time, there is a quiet sense of gratitude. Out of all the stretches of time the universe has, humanity happened to emerge during an era when Saturn's rings shine clearly in our telescopes, and when we have the means to send a spacecraft to dive among them. It is not that the planet chose to offer us a gift. Saturn follows its own physics, its own gravity and chemistry and motion. But the alignment of our brief human window with the life of those rings feels, in a gentle way, lucky. Because we were here, and because we cared enough to build and launch Cassini, we were able to see this world not just as a distant dot, but as a place with its own weather, its own puzzles, its own slow drama in the dark. All the images you may have seen of Saturn's backlit rings, of tiny moons carving paths through ice, of storms swirling over pale cloud tops, came from that one mission. All the numbers about temperatures, winds, magnetic fields, and ring particles that now fill scientific papers came from its instruments. Cassini turned a bright point of light into a layered system in our minds. When you think of Saturn now, you may picture those wide, luminous rings stretching across the black, a soft banded sphere nestled inside, small moons dotting the space around it. You may remember that underneath that beauty lies a planet that still refuses to give up all its secrets, one that bends our theories of magnetism and heat. And somewhere beneath those clouds, the atoms that once made up Cassini's body have joined the planet's atmosphere, mingling with hydrogen and helium, lost to us, but still present in that alien sky. In that sense, the mission has become part of Saturn's story, and Saturn has become part of ours. The data it sent home lives on devices and in memories, in plots and models and quiet, late-night thoughts. As long as there are people who look up and wonder, the legacy of Cassini will continue as a gentle thread through everything we are still learning about the outer solar system. On nights when the sky is clear and you find Saturn hanging faintly golden above the horizon, you might hold all of this in mind for a moment. The young rings, the hidden storms, the puzzling magnetic field, the moons with oceans and lakes, the small spacecraft that once flew there. It is all still happening, far away, whether we are watching or not. But knowing that we have watched, and that we may someday return, can be a comforting thought to fall asleep with. Jupiter is the kind of world that doesn't just sit quietly in the background of the solar system. It looms in the dark like a slow, turning lantern wrapped in bands of cream and rust, hiding storms big enough to swallow our planet whole. Its presence is so strong that even the Sun, for all its mass and power, gives a tiny nod to Jupiter's pull. And yet, when you lie back at night and see it as a single bright point above the horizon, it feels calm and distant, like a soft eye watching over the inner worlds. If you could trace its orbit across a star map, you would find Jupiter living just beyond the asteroid belt, between the paths of Mars and Saturn. On average, it sits about 778 million kilometers from the Sun, roughly 5.2 times farther out than Earth. At that distance, sunlight has spread and thinned. What feels fierce here has become a cooler, gentler glow. Jupiter takes about 12 Earth years to complete one long circuit around the Sun, so its year is stretched out and slow. The planet's axial tilt is only about 3 degrees, far smaller than Earth's. That means Jupiter doesn't lean very much as it orbits. There is no dramatic tipping of its poles toward and away from the Sun, no strong swings between summer and winter. Its cloud tops live under a fairly steady kind of daylight, more like Saturn's mild rhythm than the sharp contrast our own world knows. Still, Jupiter's shape tells you it is in motion. At the equator, its radius is noticeably larger than at the poles, a clear sign that it spins so fast its middle bulges outward. Jupiter is the largest planet in the solar system by far. If you placed it beside Earth, it would tower over us. Its diameter is about 11 times that of our planet, and its total mass is about 318 times greater. Yet for all that mass, it is not especially dense, mostly made of hydrogen and helium, like a small, failed star that never quite got hot enough to ignite. Even so, Jupiter holds almost everything that is left over after the Sun takes its share. The Sun contains about 99.86% of all the mass in the solar system. Much of the remaining fraction belongs to Jupiter alone. Its mass is about 2.5 times that of all the other planets combined. Because gravity is tied to mass, Jupiter's pull is immense. If you could stand near its cloud tops, the gravity would feel more than twice as strong as Earth's. That same gravity reaches out across the solar system, tugging on asteroids, comets, and even the orbits of the other planets. It is strong enough to tear apart fragile objects that wander too close, strong enough to gather and hold at least dozens of moons. From tiny fragments only a few kilometers wide to large worlds with their own oceans and atmospheres, Jupiter's influence on the Sun is subtle but real. When two bodies orbit each other, they both move around a shared center of mass called the barycenter. For most planets, this point lies deep inside the Sun, and the star's motion is just a small wobble. But Jupiter, with its large mass and its distance from the Sun, shifts this balance so that the barycenter actually lies just outside the Sun's visible surface. As Jupiter goes around its orbit, the Sun moves too, tracing a looping path around this shared center of mass. Here in reality, Jupiter's gravity shapes the architecture of the solar system in quiet, persistent ways. It sculpts gaps in the asteroid belt, captures wandering objects as new moons, and may have disrupted or destroyed early planetary embryos that once tried to form in the region where it now reigns. Some models suggest that, in the distant past, Jupiter's pull stirred up the orbits of countless young bodies, sending some inward to collide with the inner planets and others outward into the deep cold. Even now, its tug continues to affect worlds far away. Over long spans of time, tiny gravitational nudges accumulate, gently reshaping orbits in ways that only become noticeable when you step back and look across billions of years. At the same time, Jupiter plays a gentler role, that of a partial guardian. Its strong gravity can act like a cosmic broom, sweeping up some of the comets and icy visitors that might otherwise cross the paths of the inner planets. Long-period comets falling in from the outer reaches can be diverted, broken apart, or even ejected from the solar system entirely after a close approach to Jupiter. It is not a perfect shield. Earth has still been struck many times, but for some dangerous wanderers, Jupiter is the last encounter that sends them away for good. Even from our distance, Jupiter's presence is obvious in the sky. Though it lies about 5 times farther from the Sun than Earth does, it can still shine as the third brightest natural object after the Moon and Venus. At its best, it is bright enough that on a dark, clear night, it can cast a faint shadow. With a simple pair of binoculars or a modest backyard telescope, you can pick it out easily and even glimpse its main cloud bands and some of its 4 largest moons as tiny points lined up beside it. Those bands are part of what makes Jupiter's disk so distinctive. The visible cloud layer is only on the order of a few dozen kilometers thick, made mostly of ammonia crystals and other compounds, somewhat like Saturn's. But deeper inside, warmer material is rising from below, carrying with it a stew of chemicals. When these trace substances reach the upper clouds, they are altered by ultraviolet sunlight. These altered chemicals, called chromophores, are thought to be the source of Jupiter's browns, creams, and rust-colored stripes. High-speed winds circle the planet in alternating east-west bands, so the colors are stretched into long, stable lanes. Each band sits at a particular latitude, keeping its general position over long periods, even as its color subtly shifts and its width swells or narrows. Where neighboring bands slide past one another, their winds shear and mix, driving the turbulence that gives rise to eddies and storms. The most famous of those storms, the Great Red Spot, is like a vast, slowly turning wound in the atmosphere, though at this point, it feels almost more like a birthmark. It is an enormous anticyclonic storm system, long-lived and towering above the surrounding clouds. You could set the entire Earth inside it with room to spare. We have known about it since the 1600s, and it may be even older. For centuries, observers have watched it drift slightly, brighten and fade, and change shape, but always persist. In recent decades, careful measurements have shown that the Great Red Spot is shrinking. It is still huge, but not as wide as it once was. Its color also changes over time, ranging from a deep brick red to a pale, almost salmon shade or even near white. One leading idea is that the same kinds of chromophores that color Jupiter's bands are concentrated and altered more strongly in the spot. Because this storm rises higher than many of the neighboring clouds, its upper layers are more exposed to sunlight and ultraviolet radiation, allowing those chemicals to be broken apart and recombined into reddish compounds. When conditions change, winds, upwelling, or the supply of material from below, the color of the spot can soften or intensify. Jupiter does not host just this one impressive storm. In the late 1000, 990 seconds, and early 2000s, three smaller storms merged to form a new, persistent oval that gradually took on a reddish hue of its own. This feature, often nicknamed Red Spot Jr., has so far survived close passages by its larger neighbor and has become a notable patch in the southern hemisphere. Another similar storm once wandered straight through the Great Red Spot and was torn apart in the encounter, showing that even these massive systems are vulnerable in the long run. Beneath these swirling clouds lies an interior that we cannot see directly, but whose broad outline we can infer. Jupiter is thought to be composed of about 90% hydrogen and 10% helium by number of atoms, with small amounts of methane, ammonia, water, and other trace substances mixed in. As you descend, the atmosphere grows denser and hotter until hydrogen transitions from a gaseous state to a liquid. Deeper still, under crushing pressure, that liquid hydrogen is squeezed into a metallic form, able to conduct electricity like a metal. Somewhere below that metallic ocean may lie a core of rock, ice, or a mixture of both, though its exact size and nature are still uncertain. Jupiter spins rapidly. It completes one rotation in roughly 10 hours, the fastest spin of any planet in the solar system. Because it is not a solid body, different latitudes rotate at slightly different rates. Regions near the poles take a few minutes longer to turn than the equator does. This differential rotation stretches storms into long ovals, drives jet streams, and contributes to the banded pattern we see from afar. It is easy to look at Jupiter large, bright, made mostly of hydrogen, and wonder why it is not a star. But stars are not lit by simple fire, and they do not burn like logs or gas flames. They shine because their enormous mass creates extreme pressures and temperatures in their cores, high enough to force hydrogen nuclei to fuse into helium, releasing vast amounts of energy. Jupiter, for all its size, is far too light for that. Current models suggest it would need to be roughly 70 or so times more massive to ignite sustained nuclear fusion. Its volume is not dramatically different from some of the smallest red dwarf stars we know, but its mass is nowhere near enough. There is barely any oxygen in its atmosphere to support ordinary combustion either, even if a match could somehow be lit in that dense, windy sky. Jupiter also wears a system of rings, though at first glance they are easy to miss. They are nothing like Saturn's bright, icy bands. Instead, Jupiter's rings are thin and faint, made mostly of tiny dust grains. There is a narrow, relatively bright main ring about 6,000 kilometers wide, and more diffuse, wider structures stretching farther out. The dust that feeds these rings appears to come from small inner moons, constantly bombarded by micrometeorites that knock material off their surfaces. One feature in the main ring, sometimes called the Meti notch, marks how the tiny moon Meti and its companions help shape the dust around them. Surrounding all of this, the rings, the clouds, the moons, is Jupiter's powerful magnetic field. Generated by the motion of metallic hydrogen deep inside, this magnetosphere is about 14 times stronger at the cloud tops than Earth's field is at our surface. It is the strongest planetary magnetosphere in the solar system, second only to the more complex magnetic regions of the Sun itself. This field carves out a vast cavity in the solar wind and traps charged particles in intense radiation belts. As on Earth, the magnetic field guides some solar and local charged particles toward the poles, where they collide with the upper atmosphere and produce glowing auroras. In infrared and ultraviolet images, Jupiter's polar ovals shine like delicate crowns. Unlike on Earth, however, Many of these auroras are influenced not only by the Sun, but also by the motion and interaction of Jupiter's moons and its own plasma environment. The four largest moons, Io, Europa, Ganymede, and Callisto, orbit well within this magnetosphere, sheltered from the direct blast of the solar wind by Jupiter's protective bubble. But sheltered does not mean safe. Jupiter's trapped radiation is fierce. Space near the planet is wrapped in belts of energetic particles that can quickly damage electronics and harm living tissue. The innermost large moon, Io, plows straight through some of the strongest regions of this radiation. At its surface, the daily dose would be far beyond what a human body could tolerate. Anyone standing there without protection would receive a lethal exposure in a matter of hours. Beyond those four major moons, Jupiter hosts many smaller companions. At last count, dozens of natural satellites had been identified, many of them less than about 10 kilometers across. The four Galilean moons, first seen by Galileo through an early telescope, remain the most remarkable. Io is a restless volcanic world. Europa likely harbors a global ocean beneath its icy crust. Ganymede, the largest moon in the solar system, exceeds Mercury in diameter, and Callisto is a heavily cratered, ancient-looking body with its own quiet secrets. From time to time, Jupiter reminds us of its role as both a threat and a protector when something slams into it hard enough to be seen from Earth. In infrared or visible light, an impact can show up as a bright flash, followed by a dark bruise in the clouds, where debris and heat disturb the atmosphere. Events like this are a reminder that space is still full of wandering objects. If an impactor of similar size had struck Earth instead, the consequences could have been catastrophic for our world. Instead, it vanished into Jupiter's vastness, leaving only a brief mark on that enormous, swirling face. So when you think of Jupiter, you can picture a giant, fast-spinning sphere of gas, banded and stormy, ringed with faint dust, wrapped in a magnetic field so strong it shapes the space around it. You can picture its moons moving in quiet procession, some icy, some volcanic, some hiding oceans in the dark. And you can picture the way its gravity reaches across the solar system, sometimes hurling objects outward, sometimes pulling them in, sometimes, perhaps, standing between us and something that might have changed Earth's story entirely. All of that drama, gathered into a point of steady light, you can see with your own eyes on a clear night, while the rest of the world around you is drifting toward sleep. Farther out in the dark, beyond Jupiter's storms and Saturn's rings, there is a world that looks calm at first glance. Uranus hangs there as a small bluish-gray disk, quiet and cold, as if nothing much is happening. But the longer you stay with it, the more it feels like one of the strangest planets we have, tipped over, distant, and quietly breaking many of the patterns the other planets follow. Even its name stands a little apart. Most planets carry Roman names, but this one reaches back to the Greek god of the sky, Uranus, later turned into the Latinized form we use now. Under that small awkwardness is a planet named for the sky itself, turning oddly in the dark. Uranus is the seventh planet from the Sun, the second to last major planet. It circles the Sun at an average distance of about 19.2 astronomical units, more than 19 times farther out than Earth. Its path is slightly stretched, so over the course of its orbit, its distance varies by about 1.8 astronomical units, the largest swing among the outer giants. Out there, sunlight has thinned to a weak glow. The top of Uranus's atmosphere sits near -220 degrees Celsius, which makes it, by temperature, the coldest of the giant planets. A year on, Uranus lasts about 84 Earth years. When astronomers first tracked its motion, they noticed that it did not follow quite the path their calculations predicted. The orbit seemed to be tugged gently out of place. The simplest explanation was another planet, farther out, whose gravity was pulling on Uranus. Using only those small deviations, scientists worked out where this unseen world should be, and when telescopes turned that way, Neptune appeared. The feature that makes Uranus most immediately different, though, is the way it spins. Most planets lean a little as they rotate, like tops, but still spin more or less upright compared to the flat plane of the solar system. Uranus is almost lying on its side. Its axis is tilted by about 97 degrees, so instead of spinning like a top, it rolls like a ball along its orbit. One pole can face almost directly toward the sun for years at a time, while the other pole spends those same years in unbroken night. This extreme tilt creates seasons unlike anything on Earth. During a solstice, one hemisphere is locked in continuous daylight, with the sun circling low in the sky, while the other hemisphere is trapped in a long polar night. A thin band near the equator experiences something like a normal day-night cycle, and even there, the sun only just climbs above the horizon. Around an equinox, Uranus's orientation lines up so that the sun shines more evenly over the equator and both hemispheres. And for a while, the planet has a more familiar pattern of rising and setting. Uranus passed such an equinox in 2007 and has been slowly drifting back toward another long, tilted season since then. Uranus rotates once every 17 hours and 14 minutes, but like the other giants, it does not spin as a solid shell. Winds in the atmosphere race along so that some regions complete a circuit in as little as about 14 hours. Because of the strange tilt, Uranus is the only planet where, averaged over a full long year, the poles receive more energy from the sun than the equator does. Yet measurements show that the equatorial regions are actually warmer than the poles. That mismatch hints at internal flows and heat transport we do not yet fully understand. Somewhere inside, warmth is being moved around in ways that hide the simple pattern of sunlight. As for how Uranus ended up on its side, the leading idea is that something large hit it. Early in the solar system's history, when young planets were still jostling for position, a body, perhaps roughly the size of Earth, may have crashed into Uranus and knocked its axis over. Models of such an impact can reproduce the extreme tilt and may help explain some of the planet's internal layering and the arrangement of its moons. The details are still being worked out, but the basic picture is a gentle-looking world with a violent past. Among the four giant planets, Uranus is the least massive, with about 14.5 times Earth's mass, compared to Neptune's roughly 17. Its diameter, about 50,700 kilometers, is just a little larger than Neptune's and about 4 times that of Earth. Spread over such a volume, its mass produces a surface gravity only slightly less than ours, about 0.89 times Earth's gravity. If there were a solid surface for you to stand on, your weight would feel familiar, even though everything around you would be utterly different. Inside, Uranus is not simply a big ball of gas. Most models show a small rocky core made of silicates and heavier material, surrounded by a thick mantle of water, ammonia, and methane in high-pressure forms, often called ices. In the deep interior, temperatures rise to several thousand degrees Celsius, and pressures become enormous. So this mantle behaves more like a hot, dense fluid than a solid sheet, a deep, global ocean of exotic mixture wrapped around the core. Above this lies a relatively light atmosphere made mostly of hydrogen and helium, together adding up to around half an Earth mass, topped by a thin cloud layer. The atmosphere also contains a modest amount of methane, around a couple of percent. Methane absorbs red light, while letting blue and green pass more easily. So when sunlight filters into Uranus's upper clouds and then scatters back out, the planet takes on its soft aquamarine color. That gentle blue-green hue is usually all we can see from Earth's distance, a single cool tone, hiding layers of structure below. Deeper in the mantle, where pressures are highest, some models suggest that methane molecules are squeezed and broken apart, freeing their carbon atoms. Under those conditions, carbon can be pressed into diamond. In that picture, diamond crystals may form and fall like hailstones, slowly raining down through the mantle. At the very bottom, there might even be a layer of liquid carbon with solid diamond pieces drifting in it. We cannot yet confirm this directly, but the physics that predicts it is plausible enough that diamond rain on Uranus has become one of those ideas scientists keep nearby. Uranus also carries a system of rings. They are not as bright as Saturn's, and from Earth they are almost invisible, but they are there. 13 narrow, dark bands circling the planet. The rings appear to be quite young compared to Uranus itself, perhaps around 600 million years old. Most are only a few kilometers wide. The particles that make them up are small, ranging from dust-sized grains to chunks a few kilometers across, and seem to be composed of water ice mixed with very dark, radiation-processed organic material. They reflect about 2% of the sunlight that hits them, darker than damp soil. These rings may be the remnants of moons that were shattered by impacts or torn apart by tidal forces, their debris spread out and confined into narrow arcs. In many ring systems, small moons called shepherds keep rings thin by gently tugging particles back into place when they drift outward or inward. Around Uranus, this clearly seems to be the case for only one of the rings. Why the other rings stay so tightly bound without obvious shepherds is still not fully clear. The rings were discovered in 1977 during an occultation of a distant star. As Uranus moved in front of the star, observers saw the starlight dim not just once when the body of the planet passed by, but several times before and after in a pattern of brief dips. Those repeated shadows were the signature of rings cutting across the line of sight. When Voyager 2 flew past Uranus in 1986, the only spacecraft so far to visit it imaged the rings directly. Later, the Hubble Space Telescope and other instruments found two more faint rings farther out, including one about twice as far from Uranus as what had once been thought the outer edge of the system. Beyond the rings, Uranus is surrounded by a family of moons. 27 have been identified. Unlike the mythological naming scheme used for many other planets, these moons mostly bear names taken from English literature characters from Shakespeare and Alexander Pope. They are loosely grouped into 13 inner moons, 5 major moons, and 9 irregular, more distant moons. The inner moons orbit close to the planet and interact strongly with the rings. Some of them probably supply ring material, slowly eroded by impacts, and others help shape ring edges and gaps. The largest of this group is Puck, a roughly 162-kilometer wide moon whose dark, cratered surface was captured in some detail by Voyager 2. The inner moons are crowded into a small region of space, and constantly tug on one another. Simulations suggest their orbits are chaotic over long timescales, and some of them may eventually collide and break apart, feeding fresh debris into the ring system. Farther out lie the 5 major moons: Miranda, Ariel, Umbriel, Titania, and Oberon. Titania is the largest of the group and the 8th largest moon in the solar system, with a diameter of about 1,600 kilometers. In images, all 5 appear very dark, reflecting only a little sunlight. Umbriel is the dimmest of them. Miranda is mostly water ice, while the others seem to be mixtures of water ice and darker, rocky material. Inside, these larger moons may be layered. Many models suggest they are differentiated, with dense, rocky cores wrapped in mantles of ice. Between the core and the ice, there might be regions where water remains liquid, forming hidden subsurface oceans. For now, this remains a possibility rather than a confirmed fact, but it adds a quiet sense of depth to these distant worlds. Because Uranus itself is so strongly tipped, its major moons share the same tilt. Their equators, and thus their orbital planes, are turned almost sideways relative to the Sunday. That means the moons experience the same extreme seasons as the planet. During a solstice, one hemisphere of a moon can face the sun constantly, with the star moving in a circle in the sky and never setting, while the other hemisphere stays in continuous darkness. On such a world, sunrise and sunset would be things that happen only over the span of decades, not days. Taken together, the sideways spin, the hot, deep mantle, the dark, narrow rings, the unstable inner moons, the possibility of diamond rain and hidden oceans, Uranus stops feeling like a simple, cold ball at the edge of the map. It becomes a place where familiar ingredients behave in unfamiliar ways, stretched and pressed and lit by a distant Sunday. From here, it is just a small, soft-colored point in the telescope. But wrapped inside that point is a slow, elaborate story we have only glimpsed once with a single passing spacecraft, still waiting in the outer night for someone to come back and listen more closely. Far beyond the bright lanes of Jupiter and the pale rings of Saturn, Uranus carries a small family of companions that drift in the dim light with it. The 5 large moons are only part of that story. Much farther out than Oberon, the outermost of the big ones, there is a loose group of 9 irregular moons. They do not follow the neat, circular paths of the inner moons. Instead, their orbits are stretched and tilted, hinting that they are probably captured objects, small, wandering bodies that Uranus's gravity caught long ago and never let go. These irregular moons range in size from little worlds about 20 kilometers across up to the largest Sycorax, which is roughly 200 kilometers in diameter. They are far too small and distant for us to see much detail. From our vantage point, they are dim points of light, noticed mainly because they move in ways that background stars do not. Still, they add another layer to the Uranian system, a faint outer cloud of captured stones, circling a planet that already spins in such an unusual way. When you look back toward Uranus itself, its climate and magnetic field are shaped by that extreme sideways tilt. Seasons there are unlike anywhere else. Because the planet is essentially lying on its side, its poles take turns facing the sun directly for decades. Our telescopes have only been sharp enough to see fine features on Uranus for a few decades, so we don't yet have a full picture of how it changes over an 84-year Uranian year. But even in that brief window, patterns have emerged. As Uranus moves toward a solstice, the time when one pole leans most strongly toward the sun, the polar region brightens. A luminous cap appears, sometimes with a soft collar of color around it. After solstice, as the planet drifts back toward equinox, the pole and the collar gradually dim. The best current idea is that this brightening is tied to methane clouds thickening in the sunlight. As that pole receives more energy, methane condenses into denser, higher cloud layers that reflect more light. When the sun's angle softens again, the clouds thin and the brightness fades. The exact mechanisms remain murky, but the link between season and polar glow is clear. Storms are rarer on Uranus than on Jupiter or Neptune, but they do appear. With improved telescopes, especially in infrared light, faint bands have been seen encircling the planet, subtle cousins to the bold stripes of the other giants. In those infrared views, small bright spots pop up and vanish again, storms rising through the upper atmosphere, catching sunlight at high altitudes before sinking back into the haze. These outbursts seem to be influenced by the slow seasonal changes, flaring more often as Uranus moves through equinox and solstice, when patterns of heating and cooling shift. Uranus's magnetosphere is stranger still. On planets like Earth, the magnetic field is roughly centered on the planet and tilted only modestly relative to the spin axis. Uranus breaks that pattern. Its magnetic field is not only tipped by nearly 60 degrees relative to its rotation axis, it is also offset from the planet's geometric center. The result is a lopsided bubble in space, stronger in some regions than in others, and significantly more intense near the northern magnetic pole than near the southern one. One idea is that the unusual interior of Uranus plays a role. If the hot, electrically conductive mantle of water, ammonia, and other compounds is where the field is generated, rather than a small central core, the dynamo may naturally be shifted away from the center and strongly tilted. Another possibility is that a more conventional core-driven field is being distorted by the layers above it. Either way, the field lines do not emerge in the tidy, symmetrical fashion we see at Earth. Because Uranus is so strongly tipped, its magnetosphere is dragged into this sideways orientation as well. As the planet spins and orbits, the solar wind flows past and pushes the field into a long tail. Instead of streaming straight out into space, that tail twists into a slow corkscrew, spiraling for millions of kilometers like a coiled ribbon carried downstream. It is an invisible structure, but a reminder that even in the quiet outer reaches, the space around a planet can be wildly intricate. If you let your thoughts drift farther outward still, your attention might rest on Neptune. With the naked eye from Earth, Neptune is too faint to see, but in the mind's sky, we can keep going until we reach it. A small, deep blue world, circling even farther from the Sunday. It is the smallest of the giant planets and the most distant, yet in many ways, it may be the most restless. Neptune's story with us began not through a telescope, but through mathematics. After Uranus was discovered and its orbit carefully mapped, astronomers realized that it did not follow quite the path Newton's laws predicted, if only the known planets were tugging on it. Tiny discrepancies in its position pointed to an unseen influence. Using those deviations as clues, a French mathematician worked out where a hidden planet should be, and when observers pointed a telescope to that region of sky in 1846, Neptune was found remarkably close to the predicted spot. Within days, its largest moon, Triton, was also discovered. For many decades after that, Neptune remained a distant dot. Its great distance and small apparent size made it hard to study. Ground-based telescopes could not easily resolve details through Earth's own shimmering air, It was only when Voyager 2 swept past in 1989 that Neptune truly came into focus. Suddenly we could see the planet's true color, confirm that it has rings, glimpse storms and bands in its atmosphere, and count a surprising number of moons. Neptune now stands as the 8th and outermost major planet. On average, it orbits about 30 astronomical units from the Sun, roughly 4.5 billion kilometers. At that distance, sunlight has spread and weakened so much that it is about 900 times dimmer than the light we feel at Earth's orbit. A year there lasts around 165 Earth years. So since Neptune's discovery, we have seen only a single full circuit and a bit more. Even in that thin light, seasons exist. Neptune's axial tilt is about 28 degrees, not far from Earth's tilt, so the geometry of its seasons is familiar. The big difference is the time scale. Each of the 4 seasons lasts roughly 40 Earth years. Right now, the southern hemisphere is in a kind of spring. That side of the planet leans a little more toward the Sun and appears noticeably brighter in some wavelengths. The extra sunlight is small in absolute terms, but enough to warm the southern regions by about 10 degrees compared to the rest of the planet. That slight warming allows frozen methane to escape from deeper layers and reach higher into the atmosphere. In the southern latitudes, more methane makes its way into the stratosphere, where it reflects sunlight and brightens that region. Elsewhere, where the air stays a bit colder, methane remains locked lower down in the troposphere and has less effect on the visible glow. Despite its distance, Neptune's atmosphere is anything but calm. It hosts the fastest winds measured on any planet. Near the equator, westward jet streams can reach speeds of around 2,000 kilometers per hour, close to supersonic for those conditions. Many of these winds blow backwards relative to the planet's rotation, a retrograde flow that wraps dark and light bands around the globe. Within those bands, enormous storms arise. When Voyager 2 flew by, it saw a large, dark oval in the southern hemisphere, the Great Dark Spot, roughly the size of Earth. A smaller storm, the Small Dark Spot, churned nearby. In the weeks before the flyby, that smaller storm changed from dark to much lighter, hinting at rapid changes inside. Years later, when the Hubble Space Telescope looked for these features again, they had vanished. New dark spots have since appeared and faded in other regions. High, bright clouds of methane ice also come and go, racing along with the winds. Neptune's storms, unlike Jupiter's Great Red Spot, seem to be transient, intense, but not permanent. This contrast with Uranus raises a quiet question. The two planets are similar in size and basic composition. Uranus has fast winds too, but its weather is comparatively muted, its cloud patterns often subtle and pale. Why is Neptune so much more active? The faint sunlight that reaches both worlds does not seem to be enough on its own to drive such extreme winds. The clue appears to lie inside. While Neptune is the farthest planet from the Sun, it is not the coldest giant. Uranus, slightly closer in, has a lower effective temperature overall. Neptune radiates more energy into space than it receives from sunlight, meaning it has a significant internal heat source. Uranus, by contrast, emits almost no excess heat. One idea is that long ago, a large impact disrupted Uranus and allowed much of its primordial heat to escape, leaving it cool and relatively quiet. Neptune, which likely avoided such a catastrophic event, has retained more of its internal warmth. That hidden heat drives convection, stirs the deep atmosphere, and helps power the fierce winds and changing storms. Inside, Neptune is thought to resemble Uranus in broad strokes. Its atmosphere is mostly hydrogen and helium, with a small amount of methane. That methane absorbs red light, giving Neptune its rich blue color, a deeper shade than Uranus's softer cyan. Beneath the atmosphere lies a thick mantle of water, ammonia, and methane in high-pressure forms, wrapped around a rocky core. At the depths where the core and mantle meet, pressures rise to millions of times Earth's surface pressure, and temperatures soar. Under such conditions, methane may break apart, freeing carbon that can be squeezed into diamond structures. In theory, solid carbon crystals could form and fall like hail, creating a kind of diamond rain within the hot, dense fluid. Some models even suggest a layer of liquid carbon with solid diamond pieces drifting in it, though that picture remains speculative. Neptune's magnetic field adds another twist. Like Uranus, it does not line up neatly with the planet's spin. The magnetic axis is tilted by about 47 degrees and offset from the planet's center. When this was first seen at Uranus, it was tempting to blame the extreme axial tilt. But Neptune, with a more ordinary tilt, shows a similar offset field. The current thinking is that, as with Uranus, the dynamo that generates the field may sit not in a small central core, but in the broad, electrically conducting mantle. Fields created or strongly reshaped in that off-center shell would naturally emerge tilted and displaced. Even at this great distance, auroras glow faintly around Neptune's magnetic poles. They are nothing like the bright curtains of light that sweep across Earth's polar skies, and far dimmer than Jupiter's glowing ovals. The charged particles that reach Neptune are fewer and less energetic, and the odd geometry of the magnetic field guides them in unusual ways. The resulting auroras are subtle, closer to the quiet, broad arcs that instruments can detect on Earth, but human eyes cannot. They may stretch across the sky in ultraviolet or radio light, invisible to any imagined observer standing beneath them. Out there, in the far cold, Uranus and Neptune keep turning. Their tilted axes offset magnetic fields, hidden mantles of exotic fluids, and distant moons all continue their slow motions under a sun that has become a distant star. From here, Neptune will never be more than a dim idea, and Uranus only a pale point. But knowing they are out there, stormy, quiet, strange, can make the night feel larger and more gentle, as if the solar system itself were settling in around you while you drift toward sleep. Neptune's faint auroras have one last quiet secret. On Earth, the subtle SAR arcs connected to our own magnetic field usually cling to high latitudes, hidden above the polar regions. Around Neptune, similar arcs do appear, but not only near the poles. They can stretch across the middle latitudes, like ghostly rings of energy wrapped partway around the planet. To any imagined observer, they would be invisible to the eye, but in the right wavelengths they reveal that even here, where sunlight is weak and the solar wind is thin, the dance between charged particles and magnetic fields is still gently at work. If you drift outward a little, just far enough to see Neptune whole, another structure comes into view. Its rings. All 4 giant planets have them, but Neptune's are among the most elusive. They are extremely dark and sparse, made of materials so thinly spread that, against the black of space and at such a distance from the sun, they are almost swallowed by the darkness. Long exposures and careful processing reveal them as delicate, almost hesitant curves, 5 main rings looping around the planet. Closest in is the Gaia ring, a very faint, very broad band, roughly 2,000 kilometers across. Outside it lies the first distinctly bright structure, the Leverrier ring, narrow and sharp, only on the order of 100 or so kilometers wide. Beyond that, the Lassell ring forms a much wider, dimmer belt, stretching about 4,000 kilometers across, as if someone had softly smudged a line of chalk. On its outer edge sits the Arago ring, a slightly brighter ribbon, still quite thin compared to the broad hazes around it. Farthest out is the Adams ring, the most studied of the set. It is very narrow, only a few dozen kilometers wide, but relatively bright for Neptune's system. The Adams ring has a gentle tilt, and, most intriguingly, it is not uniform. Embedded within it are arcs, localized clumps of brighter material that occupy only certain segments of the ring, instead of being spread evenly all the way around. These arcs have persisted since they were first detected in the 1,980 seconds, despite the expectation that gravity and collisions should quickly smear any clumps into a smooth band. Something, perhaps the pull of nearby small moons, perhaps the subtle resonance of particles in the ring, is helping hold these clusters together. For now, the exact mechanism remains one more quiet puzzle. Beyond the rings, Neptune is circled by a small, varied family of moons, 14 that we know of. Their names come from water deities in Greek mythology, a gentle nod to the sea god whose Roman name the planet carries. Among them, one stands out so strongly that it dominates the system: Triton. Triton is not only Neptune's largest moon, it contains most of the total mass of all the others combined. In images, it wears a pale, textured face with sweeping patterns and patches of soft color that can look almost like frost and dried clay. Some areas show a burnt orange tint from complex organic molecules altered by radiation and sunlight. It may be one of the most strikingly patterned moons in the solar system. Its orbit tells a deeper story. Triton moves in a retrograde direction, circling Neptune opposite to the planet's rotation, and its path is tilted with respect to Neptune's equator. This combination strongly suggests that Triton did not form in place alongside Neptune. Instead, it was likely captured a large object from the outer solar system, perhaps once very similar to Pluto, that fell into Neptune's gravitational sphere and lost enough energy to be bound. Such a capture would not have been gentle. Triton's arrival and the reshaping of its orbit would have disturbed any earlier moons, pulling on their paths, stirring up resonances, and possibly driving some to collide. Those ancient collisions could have shattered smaller moons, spreading debris that later settled into the ring system we see today. In that sense, the faint rings may be made from the rubble of earlier companions, reshaped by Triton's long, slow fall into its present orbit. Triton itself is larger than Pluto and has a thin atmosphere of nitrogen with traces of other gases. When Voyager 2 flew past, it saw hazy layers and faint clouds drifting above the surface, hinting at an active world. Dark streaks across the terrain may mark past geysers, where sublimating ices burst upward and fall back as frosty deposits. For a moon so far from the sun, Triton is surprisingly alive. The next largest moon, Proteus, has its own kind of quiet peculiarity. It is roughly 400 kilometers across, larger than Saturn's small, spherical moon Mimas. Yet Proteus is not quite round. Its shape is irregular, with large craters and blocky outlines that suggest it never fully relaxed into a smooth ball under its own gravity. Past impacts have carved and battered its surface, and it seems likely that Proteus lies near the threshold where gravity is strong enough to pull an object into a sphere, but impacts and internal structure have kept it from completing that transformation. Closer to Neptune, The inner regular moons move in compact orbits near the rings. Some likely act as shepherds, their gravity subtly sculpting the edges of rings and gaps. Others may supply dust and debris, their surfaces slowly worn by tiny impacts, feeding the faint bands of material that circle their planet. Farther out still, beyond Triton, lie the outer irregular moons. Their orbits are stretched, tilted, and in many cases retrograde, indicating that they, too, are probably captured wanderers. Some travel in the same direction as Neptune's rotation, others against it, each tracing a long, slow path around the planet. At the very edge of Neptune's gravitational influence, the outermost moons take extraordinary lengths of time to complete a single orbit. Some of these distant companions need around 25 years just to circle Neptune once. They lie near the boundary of Neptune's hill sphere, the region of space where the planet's gravity dominates over the Sun's. Because Neptune is already so far from the Sun, this sphere is especially large. The Sun's grip is weaker out here, and Neptune can hold on to objects at great distances, provided they move slowly enough and happen to be captured in just the right way. When you step back in your mind and hold all of this at once, the faint rings with their mysterious arcs, the captured giant moons circling backward, the irregular outer satellites drifting at the edge of Neptune's reach, you see that even in the cold, thin light of the outer solar system, complexity and motion are everywhere. Nothing is truly simple. Even a dim, distant planet carries a history of collisions, captures, tides, and reshaped orbits written into the paths of tiny moons and the distribution of dark dust. And then, if you let your thoughts drift from Neptune inward again, past Uranus with its sideways spin, past Saturn's bright rings and hidden storms, past Jupiter's banded face and roaring red vortex, you arrive back at the small, rocky world where you are listening. All of these giants, the gas and ice worlds, circle the same sun you see rise and set. They turn slowly in the dark, herd comets, bend space with their gravity, and hold on to their fragile families of moons. From your vantage point, they are points of light, or softly colored disks in a telescope. Yet inside each of them are oceans of metallic hydrogen, mantles of superheated ice, diamond rains, shifting auroras, and winds that never stop. They do not know you are here, watching and wondering. But because we have reached out with spacecraft and careful observations, you can lie in your own night and feel a little closer to them. Somewhere out there, Neptune's faint rings continue circling, the arcs still clumped and gleaming dimly in starlight. Triton keeps rising and setting above that distant blue horizon. Pulled backward around its planet, Uranus rolls along on its side. Saturn's rings shed a slow, invisible rain, and Jupiter's storms turn on. All of it unfolds in silence, patient and unhurried, knowing that this quiet complexity exists, far beyond our weather and our days, can be a gentle thought to hold as you let your own world fade into darkness and rest.